Okay, guys, let's get into this today. Let's say we have some function f of x here. What I want to do is, we're asking the question, how do we approximate f of x for values of x near a? So, what I would say in a case like this is, well, I know that if I'm trying to approximate this function near some value of x equals a, what I could say, and this is what we looked at last class, is that, well, I could say some approximation function, I'll call it t of x, and you'll see why I'm calling it t of x in a minute. But I could name the function t of x, and I could say, well, it's equal to the function evaluated at a plus the derivative of the function evaluated at a times x minus a. Now, what I showed you at the end of class Wednesday, this is nothing more. It comes from your y minus y1 is equal to m times x minus x1 function. That's all this is. The change in the change in y is equal to the slope times the change in x, and where your y1 value, your x1 y1 is your a f of a value in there. So I could say, oh, okay, this is a linear equation. This line t of x would give me something like that. It would find the slope of the tangent line to the curve at the point A. And I could say, well, is that going to be a good approximation near A? And I said, well, for values of x right around A, yes, it is a good approximation. But soon thereafter, it becomes a horribly inaccurate approximation. So I want something to do a better job than simply a line. So what, in the early 1700s, and we don't have an exact date, that's why I'm saying vaguely in the early 1700s, an English mathematician, I'll just say Brooke Taylor, developed the following concept, and this is a concept you will be using throughout the rest of your math classes, I promise. This is not a one-time only thing. Developed this theorem called Taylor's theorem. He said, and the reason I'm using the capital T is for Taylor's theorem. T of, and in fact, I need to say T of n, sorry guys, T sub n is equal to, this represents the nth Taylor approximation. What we know whenever we get to Taylor approximations, the higher n is, the better the approximation. But the bad side of that, you think, oh, well, why not just make n equal some huge number? Also, the higher n is, the more painful it is to get that approximation. So you kind of want to level difficulty with accuracy level whenever you're doing these Taylor polynomials. So I'll say the nth Taylor polynomial is f of a plus, I could say, well, the derivative evaluated at a divided by 1 factorial times x minus a to the first. Right now you think, well, that's the exact same thing as you have above. Ooh, and this first one, I could have said, I'm going to write it in up here, this first one could have been f of a over 0 factorial times x minus a to the 0. That's the same thing as that term. Oh, I'm blindly using the notation factorial. Is everyone comfortable with the notation factorial?
I thought you were going to explain it after.
Okay. Factorial, what that is, if I say n factorial, I'm not just shouting n at you. N factorial means It's n times n minus 1 times n minus 2 times n minus 3, all the way on down to times 3 times 2 times 1. So for example, if I start counting with factorials, and this is weird, 0 factorial, in order for the system to work, it has to be defined to be 1. Doesn't make sense, I know. 1 factorial is 1. 2 factorial, 2 times 1, 2. 3 factorial, 3 times 2 times 1, 6. 4 factorial, well, 4 times 3 times 2 times 1, 24. 5 factorial, 5 times 4 times 3 times 2 times 1, 120. So this usually comes from more of a statistics discussion of permutations and combinations, where if I said you have 5 numbers on pieces of paper in a hat, how many different ways could you pull those numbers out of the hat? You could say, well, I could pull the first number out 5 different ways. Whatever that number is, the first one, it's gone though. So the second one, I would only have 4 options left. So I had 5 options for the first one. I'd only have 4 options for the second one. After you pull out 2, you only have 3 options left, then 2, then 1. It comes from more of a statistics counting procedure class. If you haven't had one like that, you might have never used factorials in anything up to this point. We say, it's nothing big. But now, when I keep on going with what Brooke Taylor came up with, he said, okay, if I continue this pattern, it's only going to improve the approximation more and more. So right now I have a linear approximation. If I'd like to make it a quadratic approximation, I'll just say, well, take the derivative twice, evaluate it at A, divided by 2 factorial times x minus a to the second. Plus, I want to do a general pattern here. Well, I'll say, okay, general pattern is pretty easy to see. So you're going to take the nth derivative of this function. For the nth derivative, you always put the exponent in parentheses. That tells you how many times you're taking the derivative. So the nth derivative evaluated at a divided by n factorial times x minus a to the n. Now, what I like to do, because I don't feel examples are beneath me, I think examples are the way you work problems, I want to look at a case of this. I'll say, okay, find the Taylor series approximation. And actually, what we're doing right now is the Taylor polynomial approximation. So I'll say, find the Taylor polynomial I'll say T2 of x. That just tells you what your polynomial is going to be in terms of. And T4 of x. So I want the second Taylor polynomial and the fourth Taylor polynomial as a function of x of f of x equals the sine function at a is equal to pi over 2. Okay, now, before we even get into this problem, I need you to see the importance of it. And it's hard to see right now within this example. Okay. What we're going to be doing with this in future classes is you'll need to be able to analyze functions on intervals. Like I could be very, very curious on what's the area underneath, let's say, like the cosecant function from 0 to pi. I want to know, what's the area of the cosecant function from 0 to pi? Well, as you might know, the cosecant function is not something that we can easily integrate. We don't know. Integral of the cosecant, you'd have to flip to your back of your book to use one of those little formulas. So there are tons of functions that are integrable, but not integrable with normal procedures. So what do we do in those scenarios? We use a Taylor polynomial, because what do you know about polynomials are always super easy to integrate. You're going to end up with something like x to the fourth, x cubed, x squared, super easy to integrate. So you can take some non-integrable function, represent it with a Taylor polynomial, and then you can work with that polynomial to approximate whatever it is, whether it's the area or the slope of the curve to the derivative of the original function. No problem at all. So this is actually a very, very powerful procedure that we're doing. But in this case, why would I choose a equals pi over 2? That would be an example if I was trying to find the integral from 0 to pi, then I want my function approximated best at pi over 2. And then the further I get away from pi over 2, the worse the approximation will be. But if I do a Taylor polynomial out enough terms, that approximation is going to be pretty solid. That's my goal to prove to you today. So I'm asking for a T2 and a T4 Taylor approximation. So I'll say, well, f of x is just our sine function here. I know that the first derivative of sine is going to be cosine. Second derivative of cosine is going to take us back to the negative of the sine. Third derivative of negative sine, we know is going to be negative cosine. And then I'll keep on going down to the fourth derivative, which we know is just going to complete the cycle here. Derivative of negative cosine takes us back to sine. Every fourth derivative of the sine function completes the cycle. So now, more importantly, I need to find out, if I look up here at my Taylor polynomial, I want to evaluate the derivative at the point of interest. My point of interest is pi over 2. So I'll go ahead and say, okay, so the first one's going to be f of pi over 2. That would give me the sine of pi over 2. What's your sine function equal to at pi over 2? 1. F of pi over 2 is 1. Then you go to f prime. Well, f prime of pi over 2, that's asking you, what is your cosine function at pi over 2? 0. F double prime, pi over 2. You'd say, well, that's the negative of the sine of pi over 2. So the sine of pi over 2 is 1. It's going to be negative 1. Beautiful. F triple prime, pi over 2. Say, well, that's the negative of the cosine of pi over 2 back to 0. And then my last one, the fourth derivative, takes me back to 1. So I can say, okay, completed the cycle, 1, 0, negative 1, 0, 1. Now, whenever I start trying to find the Taylor polynomial that refers to this, I can say, well, okay, what if I ask you for just simply the first Taylor polynomial? And say, okay, let me start off at the zeroth Taylor polynomial. That'd be really wussy. You just say, well, the zeroth Taylor polynomial, then you don't even let n equal 1. It's just your very, very, very first term. You'd say, well, that's going to be, the zeroth Taylor polynomial is just going to be f of pi over 2, which we already know is 1. So if I just used one Taylor polynomial function to approximate the sine function, I get a 1. So let's think about that really quick before I move on. So I'll say, okay, the first Taylor polynomial is telling me that the sine function here, I'm going to graph the sine function, then I'll put a 1. It's saying, hey, 1 is a good approximation of this. I'm going to graph this from x equals 0 to pi, because it said I'm supposed to be most accurate at pi over 2. For my y values, I'll go, say, negative 1 to I'll go to 1.1. I want the very tip top of the screen to be above 1. So I'll go to graph. Oh, I need to make sure I'm in radian mode. Always be in radian when you graph. So here's my sine function. Here's the line. So I can say, oh, okay, this first Taylor polynomial is trying to approximate the sine function at pi over 2. At pi over 2, it does a pretty darn good job. But beyond pi over 2 in each direction, it does a pretty crappy job. So I can say, okay, oh, all right so far. Now, when I go down to my first Taylor polynomial, t sub 1, I can say my formula for the first Taylor polynomial is going to be, I know that my first term is always f of a divided by 0 factorial times x minus a to the 0 plus f prime of a over 1 factorial x minus a to the first. So that's the formula for it. The way that that works out in this problem, I'd say, well, all of that first group, x minus a to the 0, remember, anything to the 0 power is 1. So I'd have f of a, that's f of pi over 2. We already knew that was 1. We get a 1 plus the fact that f prime of pi over 2 is 0 here tells me, well, f prime of pi over 2 is 0. 0 times anything is 0. So the second term doesn't contribute anything. Both the 0 Taylor polynomial and the first Taylor polynomial are the linear function y equals 1. So that didn't contribute much yet. I go down to the second Taylor polynomial. I know the second Taylor polynomial is the first Taylor polynomial plus, I'd say, well, it's going to be adding in the derivative taken twice, the second derivative evaluated instead of a. I know a is pi over 2, so I'll say f double prime of pi over 2 divided by 2 factorial times x minus pi over 2 squared. So I'll get that the second Taylor polynomial is going to be 1 plus the second derivative evaluated at pi over 2 was negative 1 up here, guys. So I could say, well, that's going to be plus a negative 1 over 2 factorial, which is just 2, times x minus pi over 2 squared. So I can say, well, I know that the second Taylor polynomial then is 1 minus 1/2 times the group x minus pi over 2 squared. It's probably easier just to leave it as that. Now, each of these Taylor polynomials should be an improvement on the previous one. So notice, my 0th Taylor polynomial up here gave me a linear function to approximate. I'm saying this second Taylor polynomial, it better do a better job or else I've done something wrong. Every Taylor polynomial should either be as good or better than the preceding one. 1/2 times the group x minus pi over 2 squared. So notice now when I go to the graph, gorgeousness happens. You're like, yes! It took the curve of that sine function, and said, okay, I can account for that curve with a quadratic function. Now, this predicts what's happening at pi over 2 much better than 1 does, and for a longer interval. So I'd say, okay, better. But if you're thinking, I'm still not happy with that, because I see gaps in the curve there, I see gaps in the curve there. So this is the answer to the first question I asked. I wanted the T2 polynomial right there. I need to work my way up to the T4 polynomial. Do you see that the T3 polynomial is going to be the same thing as T2? Do you see why, guys? Because the first thing you'd say is T3 is equal to T2 plus the third derivative evaluated at pi over 2 but that's 0. So I'd say, I know t, the third Taylor polynomial would equal t2 of x plus the triple prime pi over 2 over 3 factorial x minus pi over 2 cubed. But I know that that's just equal to the second Taylor polynomial plus 0. So now I can work to the fourth Taylor polynomial. And I'll say, okay, the goal of this problem, the fourth Taylor polynomial is the third Taylor polynomial, which I'll go ahead and write in 1 minus 1/2 x minus pi over 2 squared plus, for the fourth Taylor polynomial, you would say it's the fourth derivative evaluated at pi over 2 divided by 4 factorial times x minus pi over 2 to the fourth power. So I already know, well, this is going to combine to be 1 minus 1/2 times x minus pi over 2 squared. The fourth derivative evaluated at pi over 2, simply 1. So this becomes 1 over 4 factorial. 4 factorial, you can see on the board there, is 24. You also, if you ever should need it, you can do 4 math. It's under the probability menu, math, arrow to the left. There's your factorial. So 4 math, arrow to the left, 4. You get your 24 that way as well. So you can say this is 1 over 24 times the group x minus pi over 2 to the fourth. Now, my goal is to see, did this improve the situation? So I'll go into y equals, and I'll go down here and I'll say, well, the fourth Taylor polynomial was this second and third Taylor polynomial plus 1 over 24 times the group x minus pi over 2 raised to the fourth power. This better be a better approximation. Here's our sine function. Oh, I was like, oh, it's terrible. There's 1. You're thinking it's not graphing it in. But it's so precise to the other function, it's graphing it right on top of it. So the fourth Taylor polynomial, you can't tell a difference from it, at least on this graphing screen. Let's say I go to 3 pi over 4 on my sine function. The sine of 3 pi over 4, square root of 2 over 2, 0.7071068. So I would like to scroll down to y3, which is my fourth Taylor polynomial, and ask it, what is that at 3 pi over 4? I know it's supposed to be 0.7071 something. Ah, gorgeous. To 3 decimal places, it's accurate. Now, I know what you're thinking. You're thinking, well, that's accurate, but it's still 0.0003 off. That's not good. Then, if you're unhappy with that accuracy level, keep on working. T5 is going to be the same thing, but T6, you would have a 6th Taylor polynomial. You might already say, well, I know that 6th Taylor polynomial, 6 factorial, if 5 factorial is 120, 6 factorial is going to be 720. It'd be 1 over 720 times the group x minus pi over 2 to the 6th. Ooh, I want to do that. So the 6th Taylor polynomial would be plus, it'd be minus, wouldn't it? Because it would be the negative of the sine. So I'd say minus 1 over 720 times the group x minus pi over 2 raised to the 6th. Now if I go in, draw out my sine function. And again, this one's going to be even more accurate than the one preceding it. Hurry up. The longer you make these, the harder it is for the calculator to draw, but that's okay. I'll hit trace, arrow to y3, 3 pi over 4. I'm expecting 0.7071. The last one was 0.7074. Gorgeousness. So, and then you might say, well, you're still on it. Keep on going. You can get as much accuracy as you want by just taking the more and more and more Taylor polynomials.
Is this how actually table is generated?
Yeah. Yeah, whenever you get the... Yeah. Now, whenever we look at some other ones through here, what if I ask you to look at the tangent function? Tangent functions are difficult because they go off to negative and positive infinity really quickly between negative pi over 2 and pi over 2. It's extremely difficult to make a polynomial. Now again, think about what I'm saying. We know that the tangent function looks like this, where this is negative pi over 2, this is pi over 2. Well, a function, it kind of looks like an x cubed function, except it goes up extremely quickly, where x cubed does not. At pi over 2, x cubed is still a rather low number. It'd be 1.57 cubed. That's not that big. So an x cubed function is going to have difficulty, any polynomial function is going to have difficulty approximating this. But let's see what we can do here. So I'll say, I want to find the third Taylor polynomial approximation for f of x is equal to the tangent of x at the point of interest is going to be a equals pi over 4. Now the closer I get to pi over 2 or negative pi over 2, the more this function is going to struggle approximating it, because it's going to have difficulty approaching infinity with just a polynomial. But at pi over 4, I know the tangent of pi over 4 is 1. It should be able to handle that pretty easily. So let's see it in this scenario. I can say, okay, my function is f of x equals the tangent of x. Oftentimes when we take the derivative, it's going to complicate with each step. This is one of those where if you went beyond the third Taylor polynomial, it would take quite a while. I think you'll see why. The first derivative, well, derivative of tangent is secant squared. What about the second derivative? The derivative of secant squared, I can say, think of the chain rule here, guys. It's secant to the second power. So I'd say bring the power down in front, 2 times the secant to the first power, times the derivative of what's inside. Derivative of secant is secant tangent, which makes this secant squared tangent. So then I'd say, okay, can we find the third derivative? We'll have to for the T3 approximation. So I'll say the third derivative here. Here's where I'm going to think of that second derivative. Here's my first group, here's my second group. So I know I'll need to think of it as, okay, this is a product rule type of problem. When I say derivative of the first, I already know what derivative of secant squared is. All of this is the derivative of secant squared. So if I tell you to take the derivative of 2 secant squared, it's just going to be 4 secant squared tangent x. So the derivative of the first is 4 secant squared x tangent x. That's the derivative of the first times the second, makes that tangent squared x, plus the first 2 secant squared x times the derivative of the second, secant squared x. So I'll say, okay, a simplified third derivative, I could say is 4 secant squared, tangent squared. I'm going to pull out a common denominator of 2 secant squared. And then say times the group 2 tangent squared plus secant squared. Makes you feel like you're back in count 1. Which is good. Yes, derivatives. Okay, so I've simplified all 3 of my derivatives down. That's not good enough. Now you've got to use your pre-cal knowledge and be able to evaluate, and I would say exact answers only, evaluate all of these at pi over 4. So we know at pi over 4, I'll draw it up here real quick, pi over 4 is a simple angle to approximate because at pi over 4 it splits the first quadrant. Both your sine and cosine are the square root of 2 over 2. So I'd say, well, I know that the tangent of pi over 4 then is 1. So I'll say this first one here, f of, remember I have to evaluate every single one of these at your value of a, which is pi over 4 in this case. So I'll say f of pi over 4 gives me the tangent of pi over 4, that's 1. The next one here, f prime is equal to the secant squared x. So I'd say, well now f prime of pi over 4, think about this with me. Secant of x, I know secant's the reciprocal of the cosine. If I said, well, take the reciprocal of cosine for me then, you'd say, well, it's 2 divided by the root of 2. 2 divided by the root of 2 is the root of 2. So I would say, in this problem, I know secant of x is equal to 2 over the root of 2, which is equal to the root of 2 times the root of 2 over the root of 2, which is the root of 2. So secant squared x down here is going to be the root of 2 squared, 2. That's what I would do. So, next one, if you plug in f prime, or sorry, f double prime pi over 4, hopefully you're thinking in the back of your mind, wow, I don't know why he said students don't like these Taylor polynomials. This is pretty cool, darn cool stuff. I truly think it is. It's not bad. F double prime of pi over 4, when I plug this in, I already know secant squared is 2. So this is 2 times 2, 4, times the tangent of pi over 4, which is 1. So I just get 4 times 1, 4. When I plug this into the third derivative, we know secant squared is 2, that's 2, so I'll say, well, that's 2 times 2, 4 times the group, 2 times tangent squared, that's going to be 2 times 1, plus secant squared, which is 2, so I'm getting 4 times the group, 4, 16. Okay. I need to use this information to find the third Taylor polynomial. So I'd say, okay, if I happen to ask for the for the zeroth Taylor polynomial, you just say, well, the zeroth Taylor polynomial, that would equal, at pi over 4, you'd say, the zeroth derivative evaluated at pi over 4 divided by 0 factorial times x minus pi over 4 to the 0. So, and you're probably thinking, why did he not just put it's f of pi over 4? Because I'm showing you the pattern here. It's always the 0th derivative, which is just your original function, evaluated at pi over 4 divided by 0 factorial, which is 1. So all that is just f of pi over 4 times 1. But that's just showing you, hey, the formula works for every single term in there. This is f of pi over 4, which we already knew is 1. So again, the function y equals 1, approximate this with the 0th Taylor polynomial. But it would not be a very good approximation. The first Taylor polynomial And I could put t1 of x because it's going to be a function of x. I could say, well, that's going to give me 1 plus the first derivative, evaluated at pi over 4, divided by 1 factorial times x minus pi over 4 to the first. You say, well, okay, this is going to be 1 plus f prime of pi over 4. That was 2. 2 divided by 1 factorial stays 2. So I'll say plus 2 times the group x minus pi over 4. So I have my first Taylor polynomial. I need to keep on going. My second Taylor polynomial. 1 plus 2 times the group x minus pi over 4. And then you say plus what constitutes the next term in the second Taylor polynomial. You'd say, well, it's the second derivative evaluated at pi over 4 divided by 2 factorial times x minus pi over 4 squared. So I can say, okay, that's going to give me 1 plus 2 times the group x minus pi over 4. And I already know that the second derivative evaluated at pi over 4 was 4. 2 factorial is 2. 4 divided by 2 is 2. So I'll say plus 2 times the group x minus pi over 4 squared. Is everyone okay with what I've got so far? I'll move on. The third Taylor polynomial. For the third Taylor polynomial, I'll just say, well, it's the second. I'll rewrite all this in a moment. But it's everything in that second Taylor polynomial plus what constitutes the third Taylor polynomial. You have to add the third derivative evaluated at the point of interest, f triple prime of pi over 4, divided by 3 factorial times x minus pi over 4 raised to the third power. Now, whenever I do that, f triple prime pi over 4, I can say, well, I'm plugging that pi over 4 into the third group. I get my 16. 16 divided by 3 factorial. You see up on the board, 3 factorial is 6. 16 over 6 is what this would be. I know 16 over 6 will reduce down to 8 over 3. So I'll say the third Taylor polynomial is 1 plus 2 times the group x minus pi over 4 plus 2 times the group x minus pi over 4 squared plus 16 over 6, which reduces down to 8 over 3, plus 8 thirds times the group x minus pi over 4 cubed. Now, my goal again is to show that this helps with the situation. Because if this is not a good approximation, we're wasting our time doing these. You might think, yeah, we are wasting our time, John. Move on. No, we're not, I promise. There is a definite point to doing these. So trying to show you on this one, the function I'm trying to approximate obviously is the tangent function, so I'll let that be y1. Let's say tangent of x. And I'm trying to predict that with this third Taylor polynomial. So I'll say, okay, in y2 I'll say 1 plus 2 times the group x minus pi over 4 plus 2 times the group x minus pi over 4 squared plus 8 over 3 times the group x minus pi over 4 cubed. Isn't it amazing how somebody came up with this formula? It's so cool. Just how it works out. It's gorgeous. Okay, but I'm saying this is the cubic function that best represents the tangent function, at least evaluated at pi over 4. So I'll say, okay, I'm going to go to the window and I know I'm interested at pi over 4. I'm going to graph this from negative pi over 2 to positive pi over 2. So pi over 4 will be about 3/4 of the way in through there. And for my y values, I'm going to go negative 5 to 5. Now, it's not imperative that you graph these out. I just wanted to show it as a demonstration. Here's my tangent function. There's my polynomial function that predicts it. Now, what's the weaknesses of this polynomial? You'll really see the weakness over here. Now remember, the point where it better best represent it is at trace pi over 4. So it's saying for the region immediately around pi over 4, this polynomial function does an excellent, or should do an excellent job of approximating the tangent function. So I'd say, well, yeah, it looks like it does a pretty decent job from 0 to probably about pi over 3 or something. Then, when the tangent function starts getting up high or really low, the cubic function struggles. So what do you do? Well, we don't have to do anything. I'm not going to force you to get any level of accuracy. I'll just say, find the third Taylor polynomial, find the second Taylor polynomial, so that's all you do. But to answer that question, what if you say, I'm not happy with that. I want it to match that curve better. Keep on going. You'd find the 4th, the 5th, the 6th. But hopefully you also see, while it's easy for me to say, keep on going. Look how complicated that derivative starts getting. So we're just at the third derivative that's already this messy. The fourth derivative would be more beautiful still. The fifth derivative, more beautiful. Sixth. I promise you, you're going to start spending 10 minutes just to do the derivative each of these times later on. So going beyond the third Taylor approximation may not, once you start reaching your, point of diminishing returns, to where the more effort you put into it, you don't gain a whole lot of better information. I would say the third Taylor polynomial is the point of diminishing returns in this problem, because the fourth Taylor polynomial, think about this with me. If I did come up with a fourth Taylor polynomial, do you think that would be a good approximation? Oh, I say no. And you think, why not? I guarantee you that if we did a fourth Taylor polynomial, it would be a fourth degree function. What's the weakness about the end behavior of a fourth degree function? It's going to be horrendous over here. On this side, it would be nice, but then you'd start to see it'd be really good for about right. Then it starts shooting up, and you'd be like, "That's horrible."
You have to do like a Taylor series for the sine and cosine and put them over each other.
Well, you could, but yeah, that's what the tangent does. So yeah. But you just have to work two independent problems, numerator and denominator.
I'm saying that if you went more accuracy, it might be less trouble to do that.
Yeah, well, and actually, I agree. It'd be easier to do your numerator and denominator, but you'd still have to do two problems like that. But yeah, I could see the benefits to doing that. Sure.
So you're just saying every time you come to an odd polynomial,
it's going to be a better and better. I don't think even. So when I said each time you do a Taylor polynomial, it gets better, not necessarily in this case. Even ones I would say are going to be horrible as far as the end behavior, because it's going to be going up. But every odd one will be significantly better than the odd one preceding it. So if you wanted, that'd be a good project. You say, do the seventh Taylor polynomial. No, I wouldn't do that to you. But if you wanted to, it'd be cool.
More points on your
Okay, moving on down through here. If we have a Taylor polynomial centered. Now, I haven't used that terminology yet, And most of the time, the book will use that terminology. If you're saying a Taylor polynomial is centered at a certain value, that just means where they want the best prediction at. So if I say a Taylor polynomial centered at x equals 0 is called a Maclaurin polynomial. I think it's another mathematician that was working with Taylor. He allowed him to receive some credit. He just said, oh, okay, the one that occurs most frequently will allow you to put your name on it. Maclaurin polynomial, and like I said, these occur most frequently. Most of the time, we want to know what happens at 0 more so than any other point. So if I'm trying to approximate a function around 0, I'll say, I want to find a general formula. I'll ask you to find m sub n. I want the nth Maclaurin polynomial for the natural log of 1 plus x. Okay. What are we going to do with this? I'm not saying I want the first, the second, the third. I'm saying I want the nth. So as you're doing this, you have to be able to find a pattern. If you can't find a pattern, you can't find the answer. So that's our goal as I'm going through these derivatives. I need to see a pattern. So I'll say, okay, the initial function. And I just need to take as many derivatives until I see the pattern. So the initial function, the zeroth derivative, is the natural log of 1 plus x. So I'll say, okay, well, what about the derivative of that? The derivative of any natural log is always 1 over whatever's inside the logarithm times the derivative of what's inside the logarithm, which is just 1. I'm going to choose to write this as 1 times the group 1 plus x to the negative 1. Now as I go through and take continual derivatives, notice what happens. Okay, so the second derivative, I'm going to think of this as chain rule. It's a group to a power. What would you do? You'd bring the power down in front, negative 1, times the group, 1 plus x to the negative 2. Technically, times the derivative of the inside doesn't amount to anything. I'll keep on going. The third derivative, you would take your negative 2 down in front, so you'd say, okay, negative 2 times 1, that's going to become a positive, and I'll have 1 times 2. And I specifically wanted to write it as 1 times 2 there, guys. Times the group, 1 plus x to the negative 3. Are you starting to see a pattern? If not, let's keep on going. We'll do as many as you need to see a pattern. The fourth derivative. What would I do? I'd bring the negative 3 down in front and multiply it. It's going to make the term in front negative. And I'll say, well, the term in front is going to be a negative 1 times 2 times 3. I know negative 6. I'm choosing not to put a negative 6. And instead write it as that. 1 plus x to the negative 4. I'll do one last one. The fifth derivative. You'd say, well, the negative 4 would come down in front. That makes it positive. I would have a positive 1 times 2 times 3 times 4 times the group 1 plus x to the negative 5. And then I'd say, okay, so if I ask you, what's the formula for the nth derivative of this function with respect to x? Well, how would I account for that alternating sign in front? Every odd derivative, it needs to be positive. Every even derivative, it needs to be negative.
plus
A
1.
-1 squared.
Negative 1
You're on the
to
right
n.
track there.
Negative 1 to the n.
Let's think about that. I like it, maybe. Is that going to do it, guys? It's close.
Right out is backwards.
So I could say,
10 plus 1.
or minus 1, either way. So this isn't good because I could say, well, when n is 1, it needs to be positive. -1 to the first, it's going to make it negative. So I just put a plus or minus 1 on the exponent then. So I'll say plus 1. And now notice when I'm taking the first derivative, when n is 1, the first derivative, this will give me -1 to the 1 plus 1, -1 squared. That's going to be a positive. What about for the second derivative? When n is 2, this would be -1 to the third, which is negative, gives me my negative sign in front. So this accounts for the sign. Now I need to account for the numbers. So the fifth derivative had 1 times 2 times 3, which is 4 factorial. The third derivative had 2 factorial. The second derivative, 1 factorial. Remember, the sign is already taken care of.
N minus 1.
N minus 1 factorial. And whenever you do an n minus 1 factorial, you need to put the n minus 1 inside of a parenthesis and say, that group, the factorial of it. So the factorial of n minus 1. And then I'd say, okay, this group is going to be just 1 plus x to the
N?
negative n. Okay. Now, so now I'm asking for the nth the Maclaurin, the nth Maclaurin polynomial. M to the n of x is going to equal, well, I can say, I know it's, the very first term has to be this times x. Ooh, if it's centered around x equals 0, it's going to be x minus 0. So I can say, well, my first term is going to be f of 0 divided by 0 factorial times x minus 0 to the 0 power plus f prime evaluated at 0 divided by 1 factorial times x minus 1, x minus 0 to the first plus the second derivative evaluated at 0 divided by 2 factorial times x minus 0 squared plus, I'll do one more and then we'll say it, etc., etc. The third derivative evaluated at 0 divided by 3 factorial times x minus 0 cubed. Say that again, please. Oh, yeah, sorry. Okay, so what happens to all of these groups when I evaluate them at 0? F of 0. I'd say, well, f of 0 is just going to give me the natural log of 1 plus 0. Natural log of 1. What is the natural log of 1? 0. F of 0 is 0. When I go to my next term, if I plug a 0 in for x, I'd say, well, f prime of 0 would be 1 over 1 plus 0. That's 1 over 1. 1. F double prime of 0. And just to make a long story short, I know this group is always going to be 1. Because x is always 0. So it's 1 to any power is 1. So I can pretty much just ignore that throughout. And I say the only thing that's going to matter is the term in front. -1. F triple prime. Be 2. F fourth derivative. Evaluated at 0 is going to be the -6. Fifth derivative. Evaluated at 0 gives us the positive 24. Now, so I'll go down to my Maclaurin polynomial and say, so the nth Maclaurin polynomial, I would at least want you to write out the first three terms and then say dot, dot, dot to the general term. So the first term is our f of 0, which was 0, divided by 0 factorial, which is 1. All of that term is 0. You don't have to put it, but just to show that I accounted for it, I'm going to. You don't have to, obviously. Plus 1 divided by 1 factorial, 1 times x minus 0 to the first. That's just plus 1x. Plus x. Plus the second derivative value, that's going to be, actually I wish I'd have put a minus sign here. So plus a negative 1 over 2, so that's going to be minus 1/2 x squared. In fact, I'm going to scribble out this plus sign and put minus 1/2 x squared. Plus f triple prime evaluated at 0, which was 2, divided by 3 factorial. That's 2 over 6. It's going to reduce down to 1/3 plus 1/3 x cubed. And then I'll say, what would my next term be? Well, my next term is going to be f4, so that's negative 6 divided by 4 factorial. Negative 6 divided by 24, so I'll put that here, minus 6 over 4 factorial, which is 24, x minus 0 to the 4th. So I say, that's going to reduce down to minus 1/4. Are you guys seeing a pattern here yet? So I can say every term, so this is my 0th term, my first term, second term, third term, fourth term. So whichever term it is, it always seems like that term, the term ends up in the denominator. The numerator is always 1. It's always alternating sign. And then that term is also in the power. If I did it with the 5th power, just to make sure. So I would predict the next term should be plus 1/5 x to the 5th. That's my prediction. Does that work? Well, I'd say, well, the 5th term would be plus 24 divided by 5 factorial. 5 factorial is 120. 24 divided by 120 will reduce down to 1/5. And then I know that this would be times the group x minus 0 to the 5th. So I can say, yes. So now the general term here is going to be plus, I need to account for the alternating sign again. So I can say, well, that's just when you have a negative 1 to a power. So if this was the 0th term, the first term, second term, third term, fourth term, I need every even term to be negative. Again, that's just the same thing as what I have up here. Over n times x to the n. And I would have put plus dot 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 and then plus that. Now, that's what you do in the general case where you have to find a specific term, a sub n, that satisfies it. Okay, now, heading into chapter 10 with you.
Quick question.
Okay.
So then, I mean, the point of this is, like, so if you're given something like the natural log of 1 plus x and asked to integrate that, you're saying that's unintegrable with the skills that we have, right? And so you can break it down into all these different terms.
Yeah. And then if you're trying to evaluate the area under this function on a certain interval, and hopefully that certain interval will be around 0 in this case, you could use the area under this function to be a very close approximation to it.
Right, and so then to step back, so every term, as we increase that exponential power there, as we go down the line, it gets closer and closer and
It's
closer.
going to better and better approximate the curve.
So when do you know when to stop?
Well, that's the tricky thing. You would have to start up front in the problem, Michael. You would have to have a required criteria. Now, we're not going to do this in this class, but you would say, well, I want it to be within 0.0001 accuracy whenever my x value goes out, you know, one value away from this. And then you would just have to check each Taylor polynomial until you get to that. And I assure you, each one's going to be a better and better approximation. If I graph this curve in just real quickly, let's see, I'll say this is the natural log of 1 plus x. And then my Taylor polynomial was x minus 1/2 x squared plus 1 over 3 x cubed minus 1 over 4 x to the 4th. I'll stop there for now and say, does this approximate it well? Let me see. Well, if I'm centering it at 0, then I'll approximate from -1 to 1. My y values I'll take from -3 to 2 should work. So here's my natural log function. This natural log function has been shifted over 1 unit. Normally it crosses at 0, 1, or sorry, at 1, 0. Here's my function trying to approximate it. That's the 4th Taylor polynomial. I can see, well, it's running into trouble towards the end areas. So all I have to do, go back, make it better. So I say, oh, well, what's the better thing here? Add 1/5 x to the 5th. I guarantee you this is going to be better. Now I hit graph. My Taylor polynomial is still having trouble in that end region, but not on the other end. Oh, yeah, gorgeous. Drew it right on top of it. So then, if you're thinking, oh, okay, what if I want to make it super good? I'll keep on going. I'll say minus 1 over 6 x to the 6 plus 1 over 7 x to the 7 minus 1 over 8 x to the 8th plus 1 over 9 x to the 9th minus 1 over 10 x to the 10th. Okay, and you're saying that's enough, John. It better not separate. Oh, no! No!
You have to go more now.
But I won't. But I think you see the point. It's a lot closer now than it was before. And it's not going to separate on that side.
Did it pay attention during the
If it
class?
does, I'm going to pull away. I don't know what I did.
It's taking forever to graph it.
That's just a...
Come on. Okay. Oh, see how gorgeously there. So the only slight thing is right there.
It's still separated.
No.
A little bit, yeah.
Well,
You can
it
barely
thickens the
see
line,
it.
But I think you see the point. You're like, no, I need to see some more. Chapter 10, guys. Yes, 10:1. So this is kind of a good thing in this class. If you found yourself starting to get possibly overwhelmed, you're like, wow, I'm to the point where I don't want to see any more Calc 2. Good news. Good news. It's like a completely different class in this chapter. Very little of your knowledge up to this point will impact you in chapter 10. That's kind of a good thing and a bad thing at the same time. It's just completely, utterly different, yet the same. He's not making any sense. So whenever we're trying to do integration, we're talking about integration is an infinite summation. Okay, what if we want to represent that infinite summation without integrals? And again, why would we want to do that? Because tons of things are not integrable, whether by formula or anything else. So we have to have other techniques to combine terms. That's what chapter 10 is about. And this first one, it's not summation, it's just sequences. So if you have a never-ending list of terms. So 10:1, sequences. Sequence is just a function whose domain is a subset of integers. I'll put our most famous sequence. I'll say, what if I just start listing out the numbers, and this is a function whose domain is a subset of numbers. So what if I said, the only numbers I'm interested in are 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55.
Did you need to perform twice?
Oh, I did. Does that look like a familiar sequence? What is it?
I don't remember.
The Fibonacci sequence.
I mean, I'm assuming it's a person.
Oh. Well, actually, his name was not Fibonacci. He was just known by the nickname of Fibonacci. Why someone would nickname somebody Hey, Fibonacci! It was actually like Louis Dalla Villa or something like that. Fibonacci was not his name, it was his nickname.
Well, in Italian, that was probably a nickname.
Yeah, I guess.
Because the other name was so much better.
Yeah, it was something like Louis Dalla Villa or something like that. But I'm not up on Fibonacci. This is the only thing he did. But pathetic. No, it's actually pretty powerful. Some applications of the Fibonacci sequence, just for fun, if you ever like look at a pineapple and the way the little pineapple spines go around, they add in a Fibonacci sequence. So the first one you'll see 3, the next one you'll see 5, the next one you'll see 8, then 13. It expands to a certain number, and then it starts going back down again as you pass it. Same thing, like if you look on a sunflower, the way the beads go around the inside of a sunflower, it expands by a Fibonacci sequence. Honeycombs, same idea. A lot of things through nature fit this Fibonacci sequence. It's kind of cool.
Count my pineapple the next time I eat.
Yes, you'll be thinking Fibonacci sequence when you eat a pineapple.
You mean all
Ruining my food.
Now, what the Fibonacci sequence is it's just a function that's set up. It says the nth term in the function is simply the sum of the 2 preceding terms. So the nth term of a sequence is just the sum of the 2 preceding terms. Now, I want to work with some non-Fibonacci sequences for now. I'll say, well, okay, what if I give you another sequence where I tell you that the nth term of this sequence is equal to 1 divided by 2n minus 1. Every sequence notation has to give you some function to account for the nth term. So I'll say this is for n greater than or equal to 1. And you always have to keep in mind, n must be integer values only. You could have negatives, not in this particular problem. So this means, in other words, 1, 2, 3, 4, ... on out. Okay? You can't say, could I plug in n equals pi into that? No, we're not dealing with pi anymore. We're dealing with integers only. Which I know you want to deal with pi. Now, what if I ask you to write out the first 3 terms of a sub n? Then I could say, well, first 3 terms. Now, I know what you're thinking. You're thinking, wow, this is easy. Yeah, I think you will think this is easy. When you plug in n equals 1, you'll get 1 over 2 minus 1. 1 over 1 is 1. The next term would be 1 over 4 minus 1, 1/3. The next term would be when n is 3, so 1 over 6 minus 1, 1/5. And I think you can see, well, it's just going to keep on going 1/7, 1/9, 1/11, and so forth. I'll say ... I only ask for the first 3 terms. Now, what if I say, I want you to find b sub n, which is equal to a sub n plus 1. And I want you to find the first 3 terms of that. Well, all you have to do is say, well, if b sub n is equal to a sub n plus 1, then the first term of b sub n, b of 1, would equal the second term of a which is going to be 1/3. The second term of B would equal the third term of A, which would equal 1/5. You'd say, well, okay, the third term of B, that'd be like putting a 4 into A, and you'd get your 1/7. Is that making sense, guys? Okay. So, for every number in B, you have to add one more to that into A. So you say B of 3 is equal to A of 4, which would be 1/8 minus 1, 1/7. Now, what if I said, okay, well, C of n is a function A sub n plus 3. Say, well, okay, then C of 1 is equal to A sub 4. A sub 4 is going to be our 1/7. C2 would equal A sub 5, which would equal 1/10 minus 1, 1/9. And C3 would equal A sub 6, which is 1/11.
I think this is just getting a little repetitive and ridiculous.
Okay.
Is that necessary? I mean, is that really necessary?
Yes and no. I'll move on. I was going to do that. What about a function B sub n that's equal to 2n minus 1 factorial? That's cool. Divided by n factorial. And I want you to list the first 4 terms of this sequence. Okay, no big deal. B sub 1. You just plug a 1 into this formula and say, well, it's going to be 2 minus 1, 1 factorial, divided by 1 factorial. Sounds like 1 to me. B sub 2. 2 times 2 is 4 minus 1. That's 3 factorial, divided by 2 factorial. 3 factorial divided by 2 factorial is just 3. The 2 factorial cancels out the 2 times 1 part of the 3 factorial, so I'll just get 3. B sub 3. You'd say, well, that's 2 times 3 is 6. 6 minus 1 factorial is going to be 5 factorial over 3 factorial, which that would equal 5 times 4. 5 times 4, 20. 4 factorial, sorry, B sub 4. We can say the numerator is going to be 2 times 4 is 8, minus 7 factorial, divided by 4 factorial. So I know 7 factorial divided by 4 factorial, that's going to be 7 times 6 times 5. 6 times 5 is 30, 30 times 7 is 210. So the first 4 terms of this sequence, 1, 3, 20, 210. Now, while it would be hard to keep on going, I mean, it's like if I just said, oh, could you predict what the 50th term is? No, not without plugging it in into the formula. But even though you don't know exactly what it is just at a second, can you see whether this sequence, if I just ask you, use common sense to tell me, is this sequence going to converge or diverge? Now, converge means it's going to reach a limiting value and equal that number forever and ever and ever. Diverge means it either goes off to infinity or negative infinity, or it never goes to any one number. Clearly, it's going to diverge. It's getting large quickly. This is going to be what's called a divergent sequence. Now, I don't just want to do the eye test on those. We need to come up with some rules. So I'll say, okay, first rule of the day. We say a sequence converges to L if the limit as n approaches infinity of a sub n. And a sub n is just the general term of the sequence is equal to some number L. Otherwise, it diverges. So now, just showing you a quick example here. Number 3. I have time for a couple more. What if I tell you the general term of a sequence is a sub n is equal to 20 over 4 minus n squared? Sorry, not 4 minus n, 4 divided by n squared. Again, I think you'll think these problems are super easy because all you have to, this goes back to Calc 1 where you use L'Hopital's rule. You could do that, or you could just use common sense. You could say, okay, what's this definition up here asking for? If the limit as n approaches infinity of a sub n is equal to some number L, it converges to that number. If it doesn't converge to some number L, it's divergent. So all I would have to do in this problem, if that's my problem, I'd say, well, the limit as n approaches infinity of a sub n becomes the limit as n approaches infinity of 20 minus 4 over n squared. I can say, well, if I plug in infinity in for n squared, what's going to happen to this 4 over n squared? 4 divided by the largest possible number in existence ever squared? That number's going off towards 0. So this is just going off towards 20. It becomes 20 minus 0. So you'd say, since it converges to a number 20, this series is convergent. And that would be the answer. You could say, even better than convergent is converges to 20. So if you go out enough terms, all the terms just start becoming 20. You say plus the 20, 20, 20, 20, 20. So go out far enough, and that will be the nth term. Okay, number 4. What if I give you a sub n is equal to 4 plus n minus 3n squared over 4n squared plus 1? Do you remember the rule for this one, guys?
There's a little,
So,
I don't know, but it's
to determine if this is converged or not, you need to take the limit. So I'll say, then I'll be taking the limit as n approaches infinity of 4 plus n minus 3n squared over 4n squared plus 1. You have a couple of options. If you're showing out your work, I wouldn't necessarily say you have to show out your work, because if you already know, like I can look at this and you're like, ooh, you can look at it. But the answer is negative 3/4. It converges to negative 3/4. Because it follows the rule, anytime the degree of the numerator and denominator is the same, you take the fraction of the leading coefficients. Some teachers would say, you've got to show me work. You can't just tell me the answer is negative 3. So how would you show work in a case like this? You have two options. You could use L'Hopital's rule, but you'd have to use it twice. This is indeterminate, but if you took the derivative, it'd still be indeterminate in the first one. Take L'Hopital's rule twice, it would work out. Alternatively, there's an algebraic solution I'll show you here. And I'm not saying I would require you to use this algebraic solution. I'm saying other teachers would, so I need to at least show you how that would work. So I would say, to work out number 4 algebraically, so I'll say 4 continued, I would take the limit as n approaches infinity. Anytime you're in a problem like this with an algebraic solution, all you have to do when the limit's going to infinity, divide through by the largest polynomial in the problem. So I'll say, divide everything by n squared. I'll say 4 over n squared plus n over n squared minus 3n squared over n squared 4n squared over n squared. All I'm doing is I'm dividing the numerator and denominator by n squared, so that's certainly algebraically legal. Now, whenever I try to reduce this, I can say, okay, this is equal to the limit as n approaches infinity, 4 over n squared. N over n squared is going to reduce down to 1 over n. 3n squared over n squared. The n squared's canceled there, and I just have minus 3. 4n squared over n squared gives me a 4 plus 1 over n squared. Now you're able to take the limit. So once you algebraically simplify, then you say, go ahead and allow n to go to infinity. By definition, any finite number divided by infinity is 0. So when I take the limit here, notice I'll drop the limit notation. My first term is 0 plus 0 minus 3 over 4 plus 0. My answer, negative 3/4. So I would say this sequence converges to negative 3/4.
So you just make all the n's zeros?
Well, any term with an n in the denominator. 0.
Okay.
Yep. This is quite a bit different from what we have been doing, isn't it?
One more.
Okay. What if I gave you a sequence where I said the nth term of the sequence
It converges to 0 or negative 3/4.
Good catch.
I was wondering if you meant to put 0.75.
No, I didn't mean to 0. I was thinking of my next problem.
Well, you don't even have to do the work.
I knew the answer.
If you could do that on the test, it'd be awesome.
You're like, oh, I just got my numbers mixed up. What about if z sub n is equal to 1/3 to the n? And think about what's going to happen here. Okay, well the nth term of this, if n is going to infinity, 1/3 to the infinity power, 1/3 times 1/3 squared is 1/9. 1/3 cubed is 1/27. 1/3 to the 4th is 1 over 81. So I'd say it's getting really small, really fast. So, and sometimes people have struggled with this. We're like, oh, I don't know. But there's really no work to show. You just have to use common sense here and say, the larger that exponent gets, the smaller this fraction gets. This answer is 0. So I can say converges. So the limit as n approaches infinity of 1/3 to the n equals 0. Thus, the series, or I should say the sequence z sub n converges to 0.
Can we just write
One.
converges? Do we have to write converges to 0? Or
Oh, it's a z. Again, I'm asking you, does this series, I keep on saying series, does this sequence, whose term has this as the general term, converge or diverge? So your homework, at least in the beginning of section 10.1, the first problems will just say, list out the first so many terms of the series. So, sequence. So this would be the square root of 1 is 1 over 1 plus 4. Your first term is going to be 1 over 5. Your second term is going to be the square root of 2 over 4 plus the root of 2. Third term, the square root of 3 plus 4 over 4 plus the root of 3. So when I'm thinking of that, is this sequence getting smaller, larger? Does it converge to any value? How do I know? Well, I think of it as a function, so I can say, well, okay, if I let the limit as n approaches infinity of the square root of n over the square root of n plus 4. Now, a difference between the way I'm working with these problems and the way your solutions manual will, and I just wanted to let you know, It's not really a difference. It's just a change of mindset. You'll notice that the author will never do that. He thinks this is poor notation. I say, oh, get over it. Here's his reasoning. You can't technically use L'Hopital on anything that's not a continuous function. A sequence is not a continuous, it's a collection of points. But what it is, it's a collection of points on a continuous function. So what he will say is he'll use the logic, he'll say, oh, the sequence a sub n are points on the curve f of x equals the square root of x over the square root of x plus 4. And then he'll say, then you'll use L'Hopital or algebraic manipulation on the square root of x over x plus 4. And you're like, why is he bringing in x's? The problem had n's. Our sequence are points on that curve. I say, I just bypass that step and say, yeah, I know they're points on the curve. Let's just work with this instead of introducing yet another variable. So I work with this. His notation is actually superior, but I'm okay with either one. Now, in this problem, can you see a technique that we already used to simplify this one? Say that again, please.
Dividing all by the square root of n.
Yeah, I like it. Or you could say, degree of your numerator denominator is 1/2, so divide by n to the 1/2, which that's just the square root of n. So you'd say, if you algebraically simplify this, you would do the following. Just like Josh said, divide through by the square root of n. Becomes the limit as n approaches infinity. Your numerator is 1, your denominator is 1 plus 4 over the root of n. And then you know you're allowed to take the limit now because anything with a term going, even the square root of infinity is infinity. 4 divided by the square root of infinity is 0. So this becomes 1 over 1 plus 0, which is our 1. Converges to 1. Now, hopefully I haven't put you into too false sense of security. Does Chapter 10 get harder? Yes, of course. It's Calc 2. But I still think it's not that bad. Even though usually sequences and series, if you ask people what their least favorite part of Calc 2 is, that's what they'll say. Hopefully you won't be saying that. So we'll be looking at that Wednesday. Oh, it's not in class. Oh, okay.